Okay, I'm going to do good morning today. So, good morning. Thank you for indulging. We're starting late today, as I think you realize. We're starting now. Thank you. Thank you for your understanding. I'll say good morning very quickly. Good morning, Joshua. Good morning, Jocelyn. Good morning, Gabriella. Good morning, Nadine. Good morning, Lunar. Good morning, Effie. Good morning, Mohammed. Good morning, Sydney. Good morning, Sinead. Good morning, Joshua. Good morning, Gabriella. Good morning, Nadine. Good morning, Norma. Good morning, Teresa. Good morning, Effie. Good morning, Sydney. Good morning, Jocelyn. Good morning, Lunar. Good morning, Zibo. Good morning, Melanie. Good morning, Angelina. Okay. Um, Thank you for understanding that we're starting late today. Now, again, very quickly, what I'm going to do is make a 15-minute video, like in an hour or so, like when we're done. I'm going to make a 15-minute video and post it separately from this class video from today. And I'm going to tell you right now what the 15-minute video, just to make up for the time, right? And I'm going to tell you right now what the 15-minute video is going to be like an overview or basic points about the midterm exam that we're going to have. Like, I mean, about logistics and expectations, like not the physics, but just so if you noticed in Google Classroom, there's an announcement about a midterm exam. I will give you a sense of that in a 15-minute video. Okay. So you'll want to watch that. Okay. So, and that's a good, that way I won't rabbit hole about all of it like today, and we'll just keep doing physics today. You will have plenty of time to ask me more. Believe me, we'll talk more about the exam, but just the overview announcement about it, I will like break down in a 15-minute video right after this, okay? And but certainly email me or text me if you have questions already, but this will not, we will prepare you for it, believe me. I'm just like putting it out there now, like when it is and how it works. Okay. Um, okay. So that's that. And good morning, Christopher, and good morning, Jean, and good morning, Chanel. So what I want to do now I know now we got two threads going on, maybe even really three. Because, like the exam will start being a thread that we'll start explicitly dealing with, but also right now I know you're in the middle, I believe, or actually, yeah. Oh, you could correct me in the chat, but like you're in the midst of like lab 4 stuff. I understand that last week when you would have had lab 4, you instead had a projectile board meeting, I think. And that was probably challenging to many of you because we haven't talked about projectiles yet in lecture. I totally understand that. And then you're going to this projectile lab soon. Correct me if I'm wrong. So I know things in lab are starting to be somewhat substantially ahead of things in lecture. They're always meant to be somewhat ahead of lecture. That's always meant to be a little bit of like that kind of challenging sequencing, but I understand that in some ways right now the gap is even larger. I get that. We're going to start closing that gap soon. So that's one thread, as I know things are happening in lab that are interesting. Another thread is that we have to get back to these homework computations, the homeworks that you've been handing in, that of course will ultimately help you with what you're doing in the lab. I get that too. And I do want to get back to those, but in order to get back to these homeworks that we're going over, and by the way, there's going to be a pause in the homeworks very soon. I think, in fact, the very next homework that's due, well, there's one more homework that's due like next week, and then after that, there will be a pause on the homeworks while we gather ourselves and try to catch up with ourselves and try to study for the midterm. So just recognize that. So, and I'll adjust the dates in the Google Classroom if necessary. But what I want to do right now for the remaining time is I want to complete the conclusion that I'm trying to bring to you from your very invigorating train of thought discussion Monday. I was so impressed and so happy with the way you guys were discussing it, like both your form and your content. Truly. Now I want to tell you, or I want to continue telling you sort of like what is ultimately meant to come out of that discussion or what was meant to come out of that thought experiment. And as we said at the end of the discussion, the train of thought experiment is an analogy. The train is a metaphor or an analogy to planet Earth. The question of whether the train is moving or not is analogous to the historically deep and fraught question of whether Earth is moving or not. The resolution of that question, I want you to know or at least the classical resolution, the Galilean resolution of the question whether the Earth is moving or not, that resolution literally becomes the backbone of what we now know as classical physics. Like I sort of said this yesterday, but I want to make clear again. I'm going to make clear in a different way. Most of you have heard of Isaac Newton. Most of you have heard of Newton's laws of motion. Oh, yes, they're at the heart of this classical mechanics, material that we are trying to learn right now. But what I want to make clear to you, and we're going to learn them, obviously, and there's like all these equations that come out of Newton's laws, and that's all in the mid 18th century and so forth. Um, but what I want to make clear to you is what Newton based the laws on is something that came before the laws. What came before Newton's laws of motion was a statement about the character of physics laws. Like in the same way that in this country, states can make laws and municipalities within states can make laws that tell people what they can or cannot do. But as you know, of course, underneath the laws that can be made by states or municipalities, there is a law of laws known as the United States Constitution, right? And I'm not making a political, I'm just like, that, like structurally, there is a law that says how laws are supposed to work. Same thing in physics. Before the laws of physics, there is a principle that says how the laws are going to work, whatever the laws are. And the principle, as we concluded Monday, the principle, which is called, Galileo's principle of relativity, or has come to be known as Galileo's principle. And arguably, that principle first gets articulated in a book in 1626 AD and then again in 1632 AD. This principle is so important. Again, I'm saying the laws of physics rest on it. It's so important. It's said many, many different ways, and interpreted many different ways throughout the course of history. And originally, it's not written in English. So, like, no way that I'm going to write it right now is exactly the way that Galileo wrote it. First, he wrote it in Italian, then he wrote it in Latin. But what I'm calling the first form of the principle is what we said yesterday, what we said Monday. We said that Galileo said that the laws of physics, whatever they are, whatever they're going to be forever, sorry, are the same. Okay, again, this is what I said yesterday, right? I want you to understand this is the principle, but this is what from here on in this class we call form number one of the principle. The first way to say it, what you're going to see throughout this class is we're going to keep developing form after form after form of this one principle. We're not going to develop different principles. We're developing or saying different ways to say this principle, different emphases on this principle, and each next emphasis in a way is a next topic or chapter of physics. Okay. And as we go from from form to form to form of this principle, our ability to do the equations or to choose equations or to relate equations increases and opens up new and new topics for us. So basically, what I'm trying to say is everything in physics from here on in, believe it or not, everything in physics 203 and 204, and frankly, modern physics, anything you've ever heard of about Einstein or, or like twin paradox or time and space dilation or like black hole, any of this crazy modern stuff, I'm telling you, it all is extensions and different forms of this one principle, the principle being the laws of physics, whatever they're going to be, are the same at all constant velocities, which if you were following Monday's discussion, that is I mean, that is a fancy way of saying the Earth could move all the time at 65,000 miles an hour, and yet we would not feel it at all. Like what, right? This is saying no matter how fast the Earth could or would be moving, it would be absolutely conceivable that we would have no sensory evidence of that. Hopefully, you see what I'm saying. Um, but if you don't, you'll see more with what I now say. But so the principle is whatever the laws are, they're the same at 100 miles an hour going north as they are at 5,000 miles an hour going east. Whatever the laws are, they're the same. That's form number one. And it's meant, by the way, why it's a principle is when we say it like that, it should sound almost self-evident. Like, if you hear me say that, the laws of physics are the same at all constant velocities. If any reaction in your brain is anything like, well, yeah, like, well, I don't even get, like, if you even think you might be confused because you're like, I don't even understand, like, what you're saying, like, duh, like, why would you even waste my time saying that? Then you get it because it's meant to be something that is so hard to argue that you can't argue it, right? That's why we're starting science with it or physics with it. But then here comes form number. So okay, we ended Monday with something like that, right? I'm saying uh, the laws. Galileo says, I don't know what all the laws are. I'm just about to start developing those laws now. And then my successor Newton will develop more, and then his successor Einstein will develop more. But like whatever the laws are of motion, they can't change from one motion to another because then they wouldn't be a law. That's what he's saying, right? But then that's form number one now. That's what we said Monday. But now I'm going to go on and say form number two. Sorry, yeah, form number two. So by number one, if you're wondering, do I memorize these? Yes. If you're going to memorize anything in this class, memorize these. And if you're wondering where does this fit into the class, the simple answer is everything I'm giving you right now in today's class is a legitimate example of a step three GDP. From here on in, whenever you are doing homeworks, and we will get back to the homeworks, or when you're doing exams, whenever you're solving a problem and you're doing the five-step method, uh, when you're wondering what counts as a step three GDP, like what am I allowed to write down before I start the work as a principle that's like always true that I'm going to relate to this problem? When you're feeling like many physics students often do, if you're feeling like I get what's going on sometimes once he sets up the math, like once the equations are set up, I kind of know what to do, i.e., I know step four, but I often don't know how to start the problem or like what I should use first. I'm telling you, every one of these forms that I'm about to write down, and they'll look more and more mathematical. These are all always legitimate ways. They'll always be true for a step three GDP. Like sometimes they'll be more useful than others. But you'll never go wrong in writing down one of these as a step three GDP. So here's form number two. Stop me if I'm going too frantically or if I'm confusing you, but form number two is this. Oops, sorry. Okay, form number two. Sorry, I'm going to just change the view. Form number two says no experiment can be designed nor performed to measure the absolute velocity of a single object through space. Now, that's a big claim. I mean, if you step back, it sounds like it's saying you can't ever do an experiment to measure the velocity of a thing. That is what it's saying. And it's interesting. Notice, I'm not like, notice we've already spent a month talking about velocity. Like this whole course, in some ways, is about velocity and acceleration. We're obsessed with velocity as physicists. And yet here I am coming along and saying that you can't do an experiment to measure the velocity of a single object. So what the heck? Well, here's what I'm saying, or here's what Galileo's saying. I'm calling it form number two because I'm saying if you really take seriously form number one, which almost sounded obvious, and by the way, form number one in some ways is like what many of you were saying in one word or another during the train of thought experiment. Form number one is saying, look, like whatever speed you're going, whatever the laws are, they're going to be the same at 100 miles an hour or 5,000 miles an hour or 0 miles an hour. That seems obvious, kind of, maybe. But then what we're saying here is, well, if that's true, if that's really true, that the laws of physics don't change from one speed to another, then that would mean that whatever speed you're going, the laws are the same. That would mean any experiment you would ever do would follow the same laws and would then result in the same result, whatever speed you're going, right? In other words, it means, say you wake up on that train of thought on the subway, or something more realistic, say you wake up on an airplane one day, or you're in an elevator like and you've spaced and it's like in the Empire State Building. So you've had time, like you spaced out, and now you're in the elevator, and you literally don't know whether you're moving or not. And then maybe you even look next to you, and like maybe you're in a big hotel, you're in the Empire State Building or in some big hotel or something. So there's like more than one elevator, like right, like so you look out, and then you see this other elevator going down or something. So you say to yourself, like, oh, okay, I guess yeah, like, that's like the white lights. You say, wait, okay, I see that thing over there moving. But then you're like, wait, I don't know though. Hold on. Is that thing sitting still and I'm moving past it? Or am I sitting still and it's moving past it and I really can't feel, I don't know. I'm wondering what's actually going on. You wonder to yourself, what is my elevator like literally doing? Not just compared to that elevator, but like what is it actually doing in the world, right? You say to yourself, so maybe you say to yourself, I'll do an experiment. Maybe I have high technology, maybe I have low technology, but I'm going to do an experiment to figure out whether I'm actually moving or not. So what would an experiment be? Well, so for example, maybe you say to yourself, okay, I don't know much about the laws of physics and they are still yet to be developed or whatever, but I know this much. When I'm standing around and I drop something, I know enough about gravity to know if I'm just standing around and I drop something, whatever I drop lands, it falls in a straight vertical line and it lands directly below my feet, right? Like I might not understand everything from lab 3 or like 9.8 but I know when I drop crap, it lands directly below my feet, like straight line. So you say to yourself, maybe, okay, if I were stationary and I dropped something, it would land directly below my feet. So, in order to find out whether this elevator I'm in is actually moving or not, I'm going to drop something. And if it lands directly below my feet, I guess I'm standing still. Like that's my experiment. And that, by the way, that's a totally legitimate. I mean, it's not a fancy experiment, but it's like totally legitimate based on the. So, and it seems like a good idea. But what this is saying, and what Galileo is saying is, well, hang on though. if you really took seriously form number one, if you really believe that the laws are the same no matter what, like law, for example, of gravity, no matter what level at which you know the law or whatever, if you believe the law of gravity is the same, whatever speed you're going, then then if you were standing still in a parking lot, yes, something would fall directly below, would land directly below your hand if you drive. But if you believe form number one, that's also what would happen if you were moving 100 miles an hour. If the laws are the same, then the experiments work out the same, is what this is saying, right? And of course, again, you know this is true because if you ride airplanes, you confidently have no when the airplane has reached cruising speed and the captain says it is now safe to take off your seatbelt and move freely about the cabin or whatever. If you have to go to the bathroom, you go to the bathroom, right? You just like walk to the bathroom as though that's okay. You don't adjust your behavior or your expectations, even though you're on an airplane. You act like you're just in a hotel room, right? Or a hotel because you can. Because in your gut, you know, well, even if I don't know all the laws of physics, whatever the laws are, they're going to be the same. Whether the air, as long as the airplane's cruising at a constant velocity, the laws aren't going to change. So all experiments work out the same. So you treat the airplane as though it's still. So what this means, though, then is, oh, in the same way that you can just like walk to the bathroom without any problem, is the same way you cannot do an experiment to find out whether you are actually moving through space or not. What this is saying is you can't do an experiment to measure the velocity of a single object. It says single object, right? It's saying you if you want to know, no, really, what is this thing doing that I'm in? This airplane, this train, this elevator, this planet. What is this thing actually doing? Not compared to something over there, but what is it actually doing? What's the deal, yo? What this is saying, well, if you believe form number one, then you got to believe form number two, which is you're not going to do any experiment to find out. There's no experiment that could find that out for you. Uh, just raise. I'm about to move on, but just raise your electronic hand or something if you basically get what I'm saying so far. Cool. Okay. Cool. Thank you. Okay. Thank you, George. Thank you, Gabriella. Thank you. Lots of people with the Ziva. Okay. Awesome. Awesome. I love this class. Okay. Awesome. Okay. So then, and again, by the way, the kind of and I believe you, and thank you, Effie, and I see others. Norma, thank you. There's others too, but okay. And if you're thinking at all, like, yeah, I get it, but it seems almost too true. Like, I don't even get what the big deal is. Then you're with me. Like, it is meant to be like, yeah, it's meant to be like, I think I always thought this, but I didn't know it was like a thing or something. Right. That's kind of what Galileo's saying. He's like, dudes, we all always understood this. That's why, because they didn't have airplanes during Galileo's time, but they had boats. I mean, for real, they had boats. So he makes a lot of comparison to boats in his writings. He's like, people, like when you get in a boat, like you don't freak out. I mean, right? Boat experience is the same, whether it's docked or whether it's going out to sea. So you know what I'm saying is true. And all he's trying to argue to everybody, like, look, you may feel like the earth is not moving, but the fact is, if it were, you still wouldn't feel it. So it's not really an argument to say that the earth doesn't feel like it's moving. That right? That so then we go to form number three. Form number three. Now remember, this Galileo guy that you've heard of him for a number of reasons, right? I mean, you've heard of him in the context of the question of the Earth's moving, but you've also heard of him because he's like the grandfather or the of the scientific method, right? He's the guy that I mean, people have been doing physics for centuries, but people have been looking into the natural world for centuries before Galileo, just like they've been looking in the political world and the ethical world. And all of these different ways that people look at life are all different branches of philosophy, right? Philosophy means love of wisdom or love of thought. People have been doing philosophy for centuries, looking at stuff, thinking about stuff, writing it down. And there's different branches of philosophy. There's ethical philosophy, there's political philosophy, um, there's theological philosophy, and there's natural philosophy. It's not like Galileo is the first person to ever look at the world of space and time and write things down. But what makes Galileo Galileo, as I think you know at some level, is that he's the one that starts, he doesn't just look at the outside world. He starts making controlled measurements and controlling his environment and conditions so that so that he can hold everything still, hold many quantities constant, and just tweak one measurement slowly but surely and watch how nature responds slowly but surely with another measurement, i.e., he develops the whole notion of an independent variable and a dependent variable and relating the two in a reproducible, controllable experiment. And that's what had not been done before in this kind of a way. So Galileo starts developing a method for looking at nature in a controlled, reproducible, variable separated fashion, which we call the scientific method, right? So that starts to become the lens through which Galileo looks at truth. And in other words, what was natural philosophy now starts to break off and become science or physics, if you like, right? Which isn't the only way to look at the world, and it isn't the only version of truth that we have for the world, but it's a very specific, now specialized version of looking at the truth, and the hub of it is the experimental method. Why am I saying all this? Because Galileo just said in form number two that if you really take form number one seriously, then 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 you're never going to be able to do an experiment to show how fast something is actually going in and of itself. Or you're never going to be able to do an experiment to find out if something is moving at all in and of itself. So therefore, if we're from here on in going to split off from philosophers and call ourselves scientists, it doesn't mean the philosophers are bad, but just if we're going to start thinking along these lines, then from now on, if you can't find something in experiment, then it ain't meaningful or true in science or physics, right? So, in other words, form number three then says, form number three is now really the principle of relativity. What form number three now says is what many of you were saying right from the get-go, or certainly by the end, in the train of thought, packet, and discussion. I'm here. I'm not trying to tell you something you don't already sort of think. I'm trying to tell you that what you already sort of think, many of you, or might have wondered about before, is not just you thinking and you spinning your wheels. This is the foundation of what becomes physics thinking. By this, I mean form number three. Form number three says, all right, dudes. Well, what it says is from now on, all velocities are comparisons. It says all velocities are relative from now on. Like the simplest way to say what I'm saying in blue here is just that, is all velocities from now on are relative. That doesn't mean they're vague. That doesn't mean they're imperfect or inexact or approximate. That may also be true for other reasons, but I'm not saying that. And I'm not saying they're not trustworthy. I'm not saying they're not meaningful. Or the whole class is about like velocity and acceleration. But what I'm saying from here on in, what Galileo was saying is whatever velocity is, meters per second, all that stuff, from now on, what we got to realize is it is meaningful only as a comparison. Every velocity is always a comparison. That's what I mean by relation. A comparison is always a comparison, a relation from one object to another. No velocity is a property of a single object. All velocities are comparison between two objects. We're saying this. I cannot. I know that the reason I'm yelling, I get so excited about this because I know that most of you kind of sometimes already think that. I know that I'm not saying something I could tell by your answers in the train of thought and from experience. Many of you have already kind of thought about this. Like, I guess I'm going. Look, and I know you know this because there's a part of your brains, all of you, that absolutely treats the earth as stable and still. When you walk around from classroom to classroom or from your kitchen to, your bedroom of your apartment, when you walk around in your daily lives, you're not thinking, ooh, 65,000 miles an hour. Whoa, right? You're just like, dee, 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 dee. But then there's this other part of your brain that since third grade, if anybody just asked you, can you describe the solar system, please? This other part of your brain that's been a good, dutiful student for years would be like, well, you see, there's this Earth and it goes around like this and it's going around the sun like this, right? And like you've been, accepting that for years. Like part of your brain is like the Earth is going through. But the other part of your brain is like, I am stable. How could that be? How can you believe both at the same time? It's not you. You're not doing anything wrong, and everybody does. We all sort of believe both at the same time because what we're really believing is, well, it depends what you're comparing it to. If I compare my feet to the earth, if I compare the earth to me, it's going 0 miles an hour. If I compare the Earth to the sun, it's going 65,000 miles an hour. Or if I compare the outside of the Earth to the axis on the inside, the rotation, it's 1,000 miles an hour. Like at some level, we all know velocity is a comparison. What we're here now saying is yes, but by the way, always. Always. There's no exceptions to that. And what we're really saying here, and the part that's like sort of disturbing, the reason Galileo got into trouble, the part that it starts becoming kind of mind numbing, but is the basis of physics thinking, is that this is always true. One comparison is no better than another. Like you can say the Earth is going past the sun at 65,000 miles an hour, or you can say the sun is going past the Earth at 65,000 miles an hour. As long as neither one of them is accelerated, which gets into other technical issues because technically sort of they are, so that gets into things. But that there's no real, what I'm saying here is if you really took form number one seriously and you really take form number two seriously, then what form number three is saying is nobody is actually literally sitting still at the center of the universe. There is no center. You might even say, wait, I thought the whole point, like, well, some people think, wait, I thought we used to think the earth was the center sitting still. And then Galileo came along and showed us no, the earth is not sitting still at the center, it's going around the sun. And I thought the conclusion was that the sun is actually the center sitting still. And I'm here to say, no, no, no. Even that is not what no. The sun is the center of the solar system, which just means the sun is the center of the system that we named after the sun. But the sun is not sitting still in the center in the universe. The sun is going around the center of the galaxy at 650,000 miles an hour. Like really. And then the center of the galaxy is going around something nothing. There's nothing that's just literally the center objectively going zero and everything else is going around it. There is not that thing. That like if there were, we couldn't even, how could we even do an experiment to know that? What we're saying here from now on is all velocities are comparisons. Okay. And we're saying that because in form number two, we found out that no experiment could show otherwise. And from here on in, what makes us physicists is that if you can't find it in an experiment, it doesn't mean anything physically or scientifically. I mean, maybe it means something philosophically or theologically, but that's not our business. Okay. So I'm going to pause for a second. That's form number three. I'm totally looking at the chat. Great. Perfect. I'm looking at the chat. Hold on. Oh yeah, yeah. So a couple of things in the yeah. I'll go back. Well, okay. So one thing that's said in the chat is, wasn't this thought also shared by Copernicus? Oh, yes, absolutely. Yes, I want to make clear. Galileo is not the first person. He's not the first person to model a universe that includes an Earth going around a sun. Rather, like Galileo is not the first heliocentric universe person. Absolutely, Copernicus came before him, for example, and Galileo 100% was aware of Copernicus's work. Galileo's also not like plagiarizing or robbing credit or like Galileo is basing his work off the work of Copernicus for sure. And Copernicus was not the first. I mean, some people are more famous about this than others, but honestly, there was a Greek guy named Aristarchus who even proposed something like this, like over 1500 years before Copernicus and Galileo. The model got more and more like elaborate and thoughtful and detailed and workable and more well known by the time it got to Copernicus. Copernicus very much made this heliocentric model of the universe famous as opposed to the geocentric model, right? So you're 100% right. Copernicus comes before Galileo. Galileo's not pretending to be the first. Here's a big difference, though. One of the reasons we talk about Galileo all the time, more than Copernicus in this context, well, number one, Galileo did a bunch of other things too that really get physics off the ground. But the other thing is that Copernicus presented it as a mathematical model. Like Copernicus said, if you're trying to make predictions, which we always are in science, if you're trying to predict things like the phases of the moon and eclipses of the sun and eclipses of the moon and conjunctions of Mercury and things like if you're trying to make predictions, the more and more knowledge we have of the night sky, Copernicus said it's actually getting easier and if you it's getting harder and harder to make good predictions based on the increasing knowledge of the sky that we've been writing down for centuries. So Copernicus said it would be a lot easier to make predictions and to understand the skies if you think of the skies this way. And this way meant put the sun at the center, not the earth. So Copernicus published that, and people knew about it, including Galileo. But Copernicus was either strategic enough or humble enough or indifferent enough that Copernicus didn't say anything like this is literally the way the universe is. He just said you could think about it this way and it actually makes your life a lot easier as a computational tool, in effect. Okay. Where Galileo then goes to the next level and sort of gets himself in trouble. Galileo then says that's not just a way of looking at it. Like that reveals a very important misunderstanding that we've had about the universe. Like we've been incorrectly saying the Earth is at the center. And Galileo starts to imply, also in a strategic way, also in a careful way, but not as careful as Copernicus. Galileo starts to get into, I don't think the universe really works that way. But you're anyway. And then Galileo, and also to be really on, I don't want to wrap. The other reason that we really take why Galileo gets in trouble and Galileo becomes the big deal and sort of the father of physics, like Copernicus is like known as an astronomer. Then Galileo really starts starting physics. And by the way, sidebar, none of this is off the topic. What I'm trying to get you all to see is that actually the laws of motion on Earth that we are studying in this class, what they come from is first and foremost laws of heavenly bodies. Like, in fact, like the recognition that I'm saying for centuries, people looked up in the stars and saw in the stuff in the sky and saw how motion was taking place in the sky. And people looked down on the ground and looked how motion was happening on the ground. And there was one set of laws to describe how things were happening in the skies, and those laws tended to involve infinities and circles, like eternal circles of motion. And people would look down on the ground and develop a set of laws that tended to involve finite straight lines, like objects going for a while and then stopping in a straight line, like on the surface of the earth. What Galileo is saying for the first time, and even Copernicus did not say this, what Galileo is saying is, wait, you know what? I think it is in heaven as it is on earth. I think actually there's one set of laws and I don't know what all of the laws are, but I think there's one set of laws governing this whole thing. heavens and earth. I think earth is part of the heavens. I think earth, you might be just a rock like hurtling through space like any other rock like Venus or Mars, etc. And Galileo says, I think that there's one principle and one set of laws that's governing the whole thing. And if we go from that point of view, we're going to start understanding a lot better how to do physics on Earth. So then he starts playing with inclined planes and pendulums and all the stuff that is physics 203, in effect, right? And Galileo starts developing things like the 9.8 number and acceleration, constant acceleration equations, all the stuff you're doing. But Galileo's point is all this stuff works and develop. I discover it and test it, and it all works because I'm going from the belief that whatever's going on up there is the same as what's going on down here, and it doesn't change from one speed to the next. So, okay, that was a long, but I'm saying you're absolutely right that people came before Galileo, including Copernicus. But this now explodes with Galileo and becomes the scientific method and the principles of physics as they apply to Earth. Like Copernicus didn't do that. But great point. That was one direct chat. Also, another direct chat, a different person. Someone said, but that was great. And by the way, let me know if that acknowledged, like if that responds to what you're saying. Another person in direct chat is saying, wait, the sun still has its own rotation, but also orbits in relation to other celestial bodies? Absolutely. I'm saying yes. And if you find that interesting, I'm glad. Like, I am saying the sun is not sitting, there's no, oh, okay, cool. Thank you. There is no meaningful way to say that the sun is like an anchor in the universe. It's not. And we don't believe in it. I mean, since Galileo, we can treat it as an anchor, just like you walking around in your daily life or doing labs in the lab. You can treat Earth as an anchor. We absolutely can and do, but we're just treating it. We're using the Earth as the basis of comparison for velocities when we do that. But we're not saying the Earth actually is at zero velocity. And similarly, I'm saying you can't say that the sun actually is at zero velocity. It isn't. So that's what I'm saying to everybody. Now, I'm going to go a step further to start relating this now to your labs and to the homeworks that are piling up, right? What you've been learning in class, in lecture so far, is some equations and relations to deal with constant acceleration in one dimension, right? That some, like we're not done, but you've been learning equations and relations to predict and compute constant acceleration situations in one dimension. What you've been noticing is in lab, starting with lab 3 that we never talked about, like the desert island thing, the graph paper thing. Starting with lab 3, all of a sudden you're talking about 2 dimensions now. You're in 2-dimensional space as of lab 3. Then lab 4, well, then these projectiles that you're talking about with Professor Liu in the board meeting, and this lab 4 thing actually tell me quickly in the chat, like, am I correct that you did a board meeting last Friday or whenever you have lab, and this week, yes, okay, thanks. And so this week you're starting lab 4, is that correct? Okay, okay, great. And I assume I'm not going to rabbit hole now. Well, I probably am, but I'm going to try not to rabbit hole now. I'm assuming that that board meeting you had at Projectos was probably hard and confusing to many of you. If many of you were like, "What? Oh, 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 you're continuing. Oh, okay, good to know. Oh, I'm sorry. Okay, 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 okay. All right, I stand corrected. Okay, so you have started Lab 4. Okay, so look, many of you might have found the beginning of Lab 4. You're almost done with it. Okay, okay. So I won't wrap it. But for any of you who's like, I don't know if you feel like it's, well, I mean, I guess just tell me the private, well, do you find that, do you sort, I don't know if I want to ask this or not. Quickly, just so I have perspective. I'm not necessarily going to, in the private chat, please, so that nobody is like embarrassed or whatever. In the private chat, I want you to rate on a scale from 1 to 5 like your comfort level with like your comprehension comfort level with what's happening in lab like with essentially with lab 4 and related stuff. In other words, one would be I have no idea what's going on. Like I'm like this close, like I'm doing it, but like I have no idea what's going on. I'm just faking it and hoping it'll all become clear someday. Five would be like, no, I mean, like I don't know if I'd want to take an exam tomorrow, but yeah, no, I'm good. I'm as good as I ever am, pretty much. And three would be like I'm neutral. Like three would be like I'm not in a panic, but I'm not saying it's really making sense to me, but I'm okay. Like just scale on 1 to 5 your lab feeling right now, just so I know. Yeah, your comfortability level. Right, right, right. Okay, okay. I'm looking and I'm taking this in. I understand it was difficult. Oh, okay. Oh, some people say difficult. Okay, okay. Okay, cool, cool. No, I appreciate your honesty. So we're okay, okay. Right. Fair enough. Oh, that's specific. I see. I'm reading everything to myself. Okay. All right. I'm not going to, so let me just say again, I hear you. And honestly, and some of you are saying like 2 or 2.5. I hear that. If you're saying 3 or 3.5, that's amazing actually. Because right now, just to be clear, if I know all this stuff and I know the curriculum and all that, and if I were in your shoes right now, and I certainly have been if I were in your shoes, I'm not even sure I'd be up to a 3, given what your experience. I know that, okay? Right now. It will get better, but I'll say two things are happening. One is the lab is a little bit ahead of the lecture, so that's always like a little scary. It's what it's supposed to be because it's science. It's not math. It's science. So we find things but also board meetings. We're going to talk about this another time, just so you know. Board meetings at first always feel really frustrating and disorganized to people. And especially when the material is like as new as that material was. Board meetings never feel satisfying while they're happening. I mean, not never, but they often don't. Just know that I know that. I don't want a rabbit hole, but it will get better because what we're here to do ultimately in 2 class of physics, we're not here to gather information. You don't need us for that. You could do that on the web at this point with Google and AI. We're here to get smarter and getting smart, really, at learning how to get smarter. And getting smarter means learning what to do when we don't know what to do. Like for real, like especially if you're going to go into science research, right? We're here to, and I'm not criticizing anybody. I'm sympathetic, but just so you know, this is not just a mess, that it's like deliberate. We're here to learn. We're here to find out to know what to do when we don't know what to do, which means we're often in the experience, especially in these early stages, of not knowing what to do. And everybody hates that feeling, everybody, including me. But we're here to learn what it's like to have that feeling and get navigated out of it. So it's a process. Anyway, that's just to say, so how does this all relate? How is it that you're supposed to be doing like two-dimensional projectiles in the lab, like something's going forward while it's falling down? Like we never learned any of that in lecture, right? Like what aren't we missing equations? Wasn't there equations that Yaverbaum was supposed to give us in lecture to describe like how to do this or something? And what I'm here to say is actually from here on in, once you really take Galileo seriously, you're going to see from here on in, a lot of times you don't need new equations. You need to apply the old equations in a relativistic way. In other words, what I'm here to say right now is form number 4. This is how, okay, to bring things into lab 4 and all that. Form number 4 of the principle of relativity. If it really is follows that, oh, hold on a second. Okay. If you really take this seriously, oh, I'm going to look in the chat in a second. And we have 10 minutes, okay, 11 minutes. If you take this seriously, that velocity is really a relation, not a property, then part of what that really means is that no one constant velocity perspective is like better than another. right? If the laws are the same at all different constant velocities, then if you're looking at a situation from a certain constant velocity perspective, that's just as legitimate as any other constant velocity perspective, right? Um, Therefore, and I will look in the chat and say, I see things happening in the chat. Just hold on 1 second. Okay. Well, I'll read my handwriting out loud. Then I'm going to look at the chat, but then I'm going to explain this. What this says is that every n-dimensional experiment or problem is, in fact, n one-dimensional experiments or problems occurring simultaneously yet independently. I'm going to read it again. Then I'm going to look in the chat. Then I'm going to explain it. It says every n-dimensional experiment or problem is, in fact, n one-dimensional experiments or problems occurring simultaneously yet independently. I want to explain that and explain how that relates to the labs and everything, but let me look in the chat for, oh, okay, I'm looking at the chat. Oh, okay. Okay, fair enough. I'm reading lab was too far back. We need to explain our answers. I didn't know what to say. I find the homeworks in lecture harder than the lab. Fair enough. Fine. I'm a three, so okay. I was a bit confused on doing the vertical part of it. Fair enough. Okay, I appreciate the honesty. I'm reading all of it. I feel like I'm always second guessing and asking for and again, I'm trying to I don't want to waste your time, so I don't want to have a whole emotional discussion about that right now. I'm just saying, I see you, I hear you, and people generally feel this way at this stage of Physics 203. You're not alone, you're not crazy, it's not your fault. It's also not our fault. Like it don't be angry at yourself or don't be too worried, but also don't be angry at us. Don't think what's going on. This whole thing is a mess. No, it is deliberate and it does get better. We're trying to teach you. I hear you. We'll get back to it, but this is the nature of the beast. Like a lot of people have heard that physics is hard. Then physics starts, and we're sort of trying to tell you that it's actually easier than you might have heard, or it's easier than you might think. But what's actually hard about it is that it's hard in an unexpected way. It's not hard like more biology, more chemistry. It's not hard like that many more formulas or that many more hours that you have to do exercises each night. It's hard because a complete left turn and going back to things that are not complicated. They're simple, but simple is not the same thing as easy. I mean, again, I could rabbit hole, but just know that if you're like a little bit like befogged right now, whether it's in lab or in lecture, you're not alone. You're not doing anything wrong. It does feel that way at this stage. We're here to get better at that. So just hang in there, basically, is what I'm saying. But now, to be more concrete and specific, and also, reach out to me personally. You can always, like, even if my office hours don't work for you, send me an email or a text and we'll set up a Zoom or a phone call. I love phone calls, actually. Like, I think, whatever, like, because I drive a lot, blah, 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 blah. So and I could even, you could just even ask me questions and be like, is this crazy or is this like the type of thing I should be confused about at this stage? And I'll be like, oh no, that's totally a legitimate, because anyway. So what this form is saying is that, wait, look, hold on. The laws of physics don't change from one perspective to another. They don't change from one constant velocity perspective to another. So they don't change from one coordinate system, one reference frame we call. You might want to write this down. Well, they don't change from one coordinate system or one reference frame to another, as long as the coordinate system or the reference frame is a constant velocity. So that means all these one-dimensional equations, like all you ever learned in this class so far is one-dimensional equations. But the reason we can in lab just throw you into two dimensions and expect you to do stuff is that what we're really saying is once you're picking up on the flavor of physics, whatever equations you know that for one dimension apply to this dimension. Well, sorry, let me say this a different way. What we're saying is when a ball goes like this, when it seems to be moving in two dimensions, really what's happening is it's moving in one dimension while at the same time, yet independently, it's moving in another dimension. We're saying that there's no real such thing as a two-dimensional problem. We're saying a two-dimensional, so when I say n here, I mean substitute any number you want. For the lab right now, the number would be 2. We're saying what looks to be a two-dimensional problem is really two one-dimensional problems that are occurring at the same time, but they're occurring independently. They're not affecting each other. The laws of physics are governing this, while the same laws of physics are governing this, and they're not interfering with each other. So the whole principle of Lab 4, as maybe many of you now know, or like the whole technique of it is, you find the amount of time that something would fall from a tabletop to a floor, right? You do a calculation, which you totally could do in lecture. I mean, I could ask this question now, or you could do that, like just how, given, constant acceleration, 9.8, all that stuff, you ask yourself, how much time would it take something to fall straight down? And then you say, okay, that amount of time is how much time this thing is going to be in the air. So you say this thing is going so fast this way for that amount of time. Okay, I guess it'll go this far. Like what we're literally saying, right? I mean, I know most of you've done this already. You use the y-axis to find the time, and you just use whatever we know from lecture in the y-axis. You independently apply physics laws to the y-axis. You get the time from the y-axis, and then you say, oh, since the other axis is happening during the same time, I'll take that t and plug it into the other axis, the x-axis, and say now the physics laws that we know from lecture are applying to the x-axis in that time. So both axes are happening during the same time, but they're not affecting each other. So you apply the laws independently to one, and you apply the law independently to the other. And the link is the time. That I'm not that obviously that doesn't do your whole lab for you or anything, but I'm saying that's from here on in, the way we navigate two dimensions is we take Galileo that seriously. That so there is no new, right? So that's why you didn't have to learn any new equations or anything. All right, you get my point. I'm looking in the chat. One second. Wait, I'm looking in the chat. Wait, okay. I think I'm just reading something that's in the direct chat. By the way, I know we have 2 minutes left, so we're going to wrap it. But this is as far as I wanted to get today, and then we'll get back to the regular homework on Monday. Um, Yeah. Okay. I'm seeing something in the direct chat from a person, and I'm hearing, I'm sympathetic. One little thing that's in this direct chat is the idea of burning through time. One thing I'll definitely admit, I definitely recognize, a lot of things we do in lab, especially board meetings, there are many things, but they won't feel time efficient. That's for sure. Especially working with a group is never time efficient. And it's very frustrating. Working with a group is one of the more frustrating elements of this whole class for most people. I totally know that. And I hated that when I was a student doing that. It's certainly not efficient, especially if you think you know how to work on your own. But efficiency isn't the goal here, to be honest. I mean, we can address this more later. We're not going for breadth, we're going for depth. we're going for trying to develop equipment that then you would have on your own later on when you are faced with absolutely new things. So we're trying to build machines, not use them here. But yeah, I agree. It's not a, and a lot of times, especially in board meetings or group work, you don't feel the instant gratification of the understanding. You realize it later in retrospect, that for what it's worth. But that, okay, anyway, I know class is over. So, but thank you for hanging in, is basically what I'm saying. We'll keep doing this on Monday. Have a great week. Just catch up with the, wherever you are in Homer, just keep catching up. And so will I. Okay, thank you. Thank you. Okay, bye.